My name is Prem. I'm an associate professor at NTU since 2015. So I have roughly completed 7 years. So before joining NTU, I worked in A-Star Singapore. And before that, I did my postdoc in Japan and my PhD in IIT Bombay in 1995. So that's a brief introduction about myself. So together with me, I have two speakers. Professor Renshaw is my collaborator. He is a Nanyang assistant professor at NTU. So he has been working in NTU since 2016. He did his PhD from NUS Singapore and he did postdoc in several universities of USA. And together with me, we also have Dr. Monalisha. So she was a PhD student at IISc Bangalore and she came to NTU as an exchange student. So during the part of her PhD, she did most of the work that we are going to discuss later. So currently she got a postdoc abroad and she'll be moving out of India very soon. So with that introduction, uh, let's get into the uh, topic today. So many of you who are in the scientific field may be familiar with watching slides and listening to the talk, whereas Twitter space usually is mostly audio based. However, if you are not familiar to Twitter space, we have also arranged some slides. My friend, Dr. Mr. Raghav, who is uh, who is one of the co-hosts, so he will help to flash the slides. So if you are new to Twitter space, if you look at the top portion of your mobile screen, you will see the slides. There will be dots. So if you click the dots, you will see the slides. Raghu, can you flash the first slide now? So basically, the flow for today is that I'll be talking about the introductory stuff. So I'll be briefly mentioning about electronics, the growth of electronics in general, and why we are moving to neuromorphic computing. What's neuromorphic computing? So I'll discuss all these basic details. And Professor Renshaw will discuss about depth of our topic today, which is a synaptic field effect transistor. So we'll be talking about the physics behind the synaptic field effect transistors. Then Monalisha will be talking about her work in the last 15-20 minutes of today's space. So can you all hear me well?
Yes.
Okay, thank you, Renshaw. So basically, electronics in general is facing two major changes in the recent past. One is that people are looking at new materials, and another trend is that artificial intelligence is gaining more uh, attention these days. So our topic today is on slightly on the materials and also slightly on the artificial intelligence. So if you look at the slide 2, or you can also go to my timeline, Prem NTU. So if you go to my timeline, I have the slides of so if you look at the slide 2, I show various devices of say 1990s. So when I was a young person, 30 years ago, at that time, if I have to listen to music, I need to carry a Walkman and a cassette, which is basically a cassette player to listen to the songs. And if I have to take photograph, then I have to carry a camera with films. And if I have to shoot video, then again I need to carry a video camera with a magnetic tape and so on. So if I have to play video, then I need a video player and so on. And the game for game, we have separate gaming devices, or we use the personal computers to play games and so on. So this was the situation 30 years ago. But nowadays we can do all this in our smartphone. So with our smartphone, we can play music, we can play videos, we can speak to people, converse with people, we can take photo, we can shoot video and play games and so on. So all this growth has happened because of the way the semiconductor industry has been growing, especially the integrated chip IC technology has been following the growth predicted by Gordon Moore of Intel company. So in 1965, Gordon Moore, who was the co-founder of Intel Corporation, so he predicted that the number of transistors in an IC integrated chip will double every year. So this growth has led to processors with higher power and so on. And this growth was possible due to the improvements in the lithography technique, which is a technique to fabricate nanostructure, the microstructure, and so on. So there is a lot of improvement in the lithography technique. As a result, we can make more number of transistors in an integrated chip every year. And in addition, the physics of the semiconductor materials also has been growing. As a result, we have been achieving integrated chip with a large number of transistors, and the number of transistors in the integrated chip has been roughly doubling every year. And this kind of growth in the electronics technology has led to miniaturization of the devices. So if you look at the old mobile phones, they used to be very big. The screen will be small, but the phone, which need to have the processor, memory, and other aspects of electronics, will occupy a lot of space. Nowadays, the screen occupies more space, and the other components do not occupy much space. So a lot of miniaturization has happened because of the growth in the Moore's law, and the performance of the electronics devices also has increased. So, for example, as I mentioned before, we need to have separate devices for separate function, but now we can have one smartphone with all the functions to satisfy most of our needs, like playing music or making phone calls, playing videos, shooting videos, and so on. So the performance improvement has happened a lot, and there's also huge reduction in the cost, say per megabyte or gigabyte of memory and so on. And we have a lot of new functions in a device. So this is one of the main impact of the growth based on Moore's law. And normally in the social media, people uh, show 10 years challenge. So they will show their old photo and new photo and say how much they have changed. So in one of my tweets, I have show 10 years challenge in semiconductors. For example, if you look at a micro SD card of 2005, so at that time, the micro SD card had a storage capacity of 128 megabytes. Whereas if you look at the similar SD card 10 years later, you would see that the SD card had a capacity of 128 gigabytes. So within 10 years, the capacity has grown like 1,000 times. So this kind of growth has happened because of the Moore's law that I was describing before. But this kind of growth in the electronics industry based on Moore's law is limited because the electronics industry is also facing physical limits. So as a result of the challenges to continue the growth based on Moore's law, people are looking at alternatives. So they are looking at a non-Moore based growth. For example, if you look at the CPUs of the computers, so they have tried to pack more cores into one CPU. So earlier days, one chip had only one processor, but these days people try to pack a dual processor, quad, which means four processors into one dice and so on. So this way they are trying to improve. So this is one way of improving the growth in the semiconductor industry. And another way to look at the growth, I mean, or manage the growth is by looking at different materials. So in that connection, the area of spintronics where I work also comes into picture. So people are trying to use magnetic materials also to improve the electronics technology. So we are trying to make new devices based on magnetic materials that can supplement the growth of the semiconductor technology. So that's one way the electronics industry is growing. Then another area which I just mentioned a few minutes ago is the area of artificial intelligence. Many of you may be surprised if I tell you that artificial intelligence is older than the internet. Even though you might be hearing artificial intelligence only recently, it has been happening for many years. Even in the 1950s, people have started working on artificial intelligence, and the artificial intelligence technology has been having its own ups and downs. And the main drive in the recent past came from the 1997 event. So in 1997, Deep Blue, which is a computer, supercomputer created by IBM, Industrial Business Mission. Um, so that machine beat a human in playing chess. So Gary Kasparov was the world champion in that time, 1997. So at that time, this computer Deep Blue played chess with him and beat the human. So that was the first event when a machine beat a human with intelligence. So that was one major breakthrough event in the field of artificial intelligence. And later, many other technologies like deep learning came. Then artificial intelligence gained wide applications. So now every major company has an artificial intelligence application. For example, Microsoft has Cortana, Samsung has Bixby, Amazon has Alexa, Apple has Siri, Google has Google Assistant, and so on. So there are a lot of artificial intelligence applications from all major companies. But one of the major challenges of the artificial intelligence is that the power consumption uh, is an issue. So if your device uses artificial intelligence, it consumes a lot of power. So this is one of the major problems, and this problem comes from the fact that the computers are designed based on an architecture. Architecture is basically where you put your processor, where you put your memory, and so on. So this architecture was created 70 years ago by a scientist called von Neumann. So for the last 70 years, we have been following the von Neumann architecture. So in this architecture, you have a CPU which is placed at one location. Then you have memory units; they are placed at another location. So if you are doing computation, the data is fetched from the memory unit into the CPU. Then after the computation, the data is sent back to the memory. So when we do when we do a lot of computation, especially when we do artificial intelligence applications, there is a lot of computation we need to do. So the data goes back and forth between the processor and the memory several times. So this causes speed issue as well as energy consumption. So if you take a desktop processor, so if you look at the CPU and the memory, basically they are separated by a distance of about 4 centimeters. So let's say if a transistor is based on 40 nanometer technology, so based on the 40 nanometer technology, if we scale, this 4 centimeter distance is equal to a human going 1,000 kilometer to fetch data. So imagine you have to go 1000 kilometer to fetch a data, then come back to your place, then do some computation, then again you have to bring the data there, then bring back and so on. So this kind of uh, thing is happening in the data flow between a processor and the memory. So this is called a von Neumann bottleneck. Um, so because of this back and forth flow of data, so flow of data is basically, it's a electric current has to flow from one place to the other place. So when electric current flows through the wire, there is heating happening. So because of heating, there is energy loss. So because of this back and forth energy flow, there is always energy loss. As a result of this and a few other issues, people are looking at the various computing technologies. So from for Neumann architecture, people are moving towards many different architecture. So there is one architecture, one computing technology called near memory computing. Then there is also something called in-memory computing. Then there are deep learning 3D architectures and so on. So maybe to explain this in a simple manner, let me give an analogy of our study table and bookshelf. For example, when we are preparing for an exam, let's say we have an exam tomorrow, then maybe the table will only have the study materials required for tomorrow's examination. Whatever we don't need for tomorrow's examination, some other books, whatever material that we have, they will be kept in bookshelf. So memory is like a uh, study table, and we can consider a CPU as a study table, uh, and the memory as a bookshelf and things like that. So when we talk about near memory computing, it's like having a bookshelf very near the study table. When we talk about in memory computing, it's like having a bookshelf just next to the table. So you don't need to walk across, you just stretch your hand, take out the book and read, then keep it back. So this kind of you bring the memory very close to the processor. So as a result, there is no mm, back and forth flow of data, no energy loss, and so on. Less energy loss and so on. So in that sense, we also are considering another computing technology, which is the topic of today, which is called neuromorphic computing. So neuromorphic computing is also called brain-inspired computing because the computing method that we are going to talk about today is based on uh, inspiration from the brain. So it's either we can call it neuromorphic computing or we can call it brain-inspired computing. So going back to the event in 1997, which I described as the competition between Gary Kasparov and the Deep Blue supercomputer. So in that event, I told you that Deep Blue computer beat Gary Kasparov. So until then, computers couldn't beat human. Only in 1997, the computers beat human in chess. So if you compare the power consumption of the supercomputer, the Deep Blue supercomputer uses megawatts of power. So it is capable of imagining an average of 200 million positions in chess per second and so on. So that kind of computation it can do. So during that process, it does it consumes megawatts of power. But if you take Gary Kasparov or any human, for example, so we consume typically 20 watt of power. Our brain operates by consuming just 20 watt of power. So there's a huge difference in terms of power consumption when we talk about intelligence. So that's why people thought that brain is very efficient device when it comes to doing intelligence operation, energy efficient device when it comes to doing intelligence operations compared to the way we operate the computer. So as I told you before, our main problem with the computing technology today is because of the von Neumann architecture. We have processor in one place, we have memory in another place, so the data flows back and forth. As a result, we spend a lot of energy in our computation. So as a result, people are looking at why not we use, we design a computer based on how brain functions. So again, if I compare the energy efficiency and the speed of a brain, so I have a slide comparing the human brain and the Fugaku supercomputer, which was demonstrated by Fujitsu in 2020. So the latest supercomputer, Fugaku supercomputer, it consumes 30 megawatt of power, which is equal to the energy required to light up 1 million LED lamps. So that kind of power is consumed by that supercomputer, and it can do 1 exaflops, which means 1 multiplied by 10 power 18 flops, which flops is basically the operations the computer carries out. Whereas brain takes only 20 watt of power, which is equal to the power required to light up one lamp. So you compare one energy required to light up one LED lamp with the energy required to one light up 1 million LED lamps. So that is the kind of power difference between a supercomputer and a human brain. So there is a huge power reduction in the way the brain operates. And if you compare the flops, flops is basically how many operations a processor does. So the number of operations does per watt of power. So brain does 5 teraflops per 1 watt, whereas the Fugaku supercomputer does only like 0.014 teraflops per watt. So there is a huge difference in the energy efficiency. As a result, people are looking at brain-inspired computing. So brain-inspired computing was proposed by a scientist called Warren McCulloch in the 1940s, but it is gaining more attention in the recent past. So before we discuss further about neuromorphic computing, which is brain-inspired computing, so let's briefly see what are the major components of the brain and what these components do and how they are arranged to achieve the computation. So we don't exactly know how the brain does the computation, but scientists know that the brains have neurons and synapses. So neurons are the processor of the brain. So they does the process inside the brain. So they are like CPUs of the brain. So basically, their operation is like they will receive inputs from other neurons. So when there is a certain chemical potential is reached, the neurons give a spike. So the spike goes out from the neuron into through the axon of the brain to a neighboring neuron. So two neurons are connected by uh, uh, something called synapse. So synapse is basically the bridge between two neurons. And the function of neurons is that when there is a flow of current from one neuron to the other neuron, say pre-neuron to post-neuron, something like that, the synapse become stronger. The connection between the two neurons become stronger. So to summarize, we have uh, neurons and synapses in the brain, and they are the basic elements of neuromorphic computing. So if you look at the brain, in the brain there are 100 billions of neurons interconnected by 1000 trillions of synapses. So synapse is basically 20 nanometer, very small gap between one neuron and the other neuron. And my co-speaker, Monalisha, will talk about the chemistry of the new synapse. I will not go into that. So basically, when we are designing neuromorphic computing, we also need to design these neurons and the synapses as electronic devices. So that's what will be covered by Professor Renshaw and Dr. Monalisha in the next few slides. But before I pass to them, I want to show one image where I show two clips. So there's a clip in the left side, and there's also a clip in the right side. So let's say the hero lives in the left side of the cliff, and there's a heroine on the right side of the cliff. Okay, so the hero wants to meet the heroine, uh, but he cannot jump. Okay, the cliffs are far away. Say, let's say they are apart from each other by a distance of 20 meter. Okay, so the hero is not a Superman, so he cannot jump across, and it's also very uh, tiring to climb down all the way from the top of the cliff to the valley, then again climb up the cliff to meet the heroine. So what he does is that he throws a rope to the side, the other side. So the heroine helps to tie it to the tree. So first time when he crosses the cliff, so he basically holds a rope uh, hanging. So with a lot of difficulty, the hero crosses the valley. So he goes to the other side of the cliff, meets the heroine, then goes back to his place at night. Okay. So when he returns, what he does is he takes another rope, then he again throws the rope, then he hangs. So when he goes like this many times, what happens is that every time if he throws a rope, then basically he can construct a bridge over a period of time. After that, he just can walk over the bridge made of the ropes. Okay, so this is the story I tell all my students before I teach a class. Uh, why I give this analogy is that so this is equivalent to the way the brain functions. So we can consider each clip as a two neuron. So we have two clips here. You can consider these two clips as two neurons, and the bridge that we formed using the rope is the synaptic connection. So first time making a connection between two neurons is not easy. So that's why we feel difficulty when we learn a new subject because the connection hasn't been formed. But once we study repeatedly, the connection forms easily, then the subject becomes easy. So this way, I mean, this is what I tell my students. So we have like tutorials, we have classroom teaching, we have assignment. So all these are things that we do to enhance and reinforce the learning. So this way, we form the connection between the two neurons by the synapses. So this is how the brain works. So when we talk about electronics, neuromorphic computing, basically we need to create neurons and the synapses as electronic devices. So that's what we are doing in our group. So we have a major funding for doing neuromorphic computing. So Professor Renshaw, we are all working together uh, to make these synaptic devices. So in our lab, we have created devices which can emulate the learning of brain. It can also emulate how the brain forgets the information, and it can also emulate how we can relearn. Suppose after we forget, we relearn the subject again, then we notice that the relearning time is much shorter than originally learning a subject. So first time learning usually takes longer time. So if you forget and relearn again, we can learn faster. And if you relearn again, then again, if you don't revise the topic, you'll forget. So that forgetting takes very long time. So basically, a brain, if we keep learning, then the information is stored for a long time, and it takes very a long time to forget. So these kind of properties we can show in the devices that we fabricate, and that's what will be discussed by my colleagues, Professor Renshaw and Dr. Monalisha, in the next few minutes. So I'll pass the mic to Professor Renshaw. Renshaw, welcome.
Hello, can you hear me?
Yes.
Okay,
Yeah.
great. Okay, I assume you can hear me because I also responded to your questions earlier. Okay, hi. Hello, everyone. My name is Renshaw. And first, thanks for the opportunity that I can discuss something with the audience. And also, at first, I admit that I'm a beginner of this field, and also a beginner. I also am new to the Twitter space. So if I make any mistakes, so please forgive me. I think I'm like to use the following several minutes to discuss the synaptic transistor. As Prof Prem has already discussed, for the neuromorphic computing, the neurons and synapses are both very important. And until now, there have been a lot of work to work on both the neurons and the synapse. In the work that we will discuss later, we mainly focus on the synapse, or you can call it synaptic device. To currently, from a device point of view, in order to fabricate a synaptic device, there are typically two types. From the structural point of view, there are two types. If you look at the slide number 21, so that's discussed the types of the two-terminal devices or two-terminal synaptic devices. Slide 22 discussed the three-terminal devices. Well, for the two-terminal devices, that's almost the beginning of the exploration of the synaptic devices because it has a very relatively simple structure. When we call it a two-terminal devices, basically from device structural point of view, there are just the two electrodes. Well, I have already shown in the slide 21 that there are top electrode and bottom electrodes. That's typically how the structure of the device is made. So one terminal is on top, one terminal is below, so that we can make the device much smaller or easier. So within the two-terminal devices, there are many different kinds of mechanisms to enable us to achieve the synaptic behaviors. I give a very brief summary about the different mechanisms. For example, there are electrochemical metallization mechanism, valence change mechanism, phase change mechanism, ferroelectric mechanism, and many other ones. For example, so the target of the synaptic devices we want is to have a distinguishable multiple states, right? So have more than two states, more than on and off. So we want to have more states, and ideally they are distinguishable. So those mechanisms enable us to do that. Sorry. So the metallization means, because the top, for example, the top electrode is a metal, and then the metal atoms would be able to enter the space between the top electrodes or bottom electrode, or between the top terminal and the bottom terminal, and forms a metallic channel. And this metallic channel would enable the current to flow, and depending on the dimension and the connection of the channels or the metallic channels, different electronic states or different conductivity will be achieved within the two terminal devices. So this is just the example as I shown on the top left schematics. There are also similarly there are many other mechanisms. For example, there are valence change mechanism. For example, by changing the valences of the atoms, the conductivity changes. Of course, we can control the number of the atom to change with the change the valences. So that means the conductivity can also be tuned to different levels. And there are also phase change mechanism. Basically, what we do is we change the portion of the phase within another phase. So for example, in the schematics, we can change the dimension of the purple region to make it grow bigger or smaller in order to then consequently we can control the conductivity. And then of course there is also ferroelectricity involves how to switch the domain, so multiple states of the domain switching. So two terminal was the let's say the pioneer of the synaptic devices, and it's also structurally it's very simple, and it has also quite many advantages. And later, as the time develops and also the knowledge of the community deepers, then people start also to achieve the three terminal devices, also explore different possible mechanisms. Well, if you look at the slide 22, also representatively presents four different mechanisms. So, for example, the floating gate transistor, electric double layer transistor, and electrochemical transistor, and the ferroelectric field transistors. So the three terminal devices has also its own advantages, which is the control of the control and also the signal passing or signal um, passing the signals through the channels are separately. So we have a more degree of the freedoms. And also, in particular, if you look at the floating gate transistors, that's a device structure completely compatible with the existing modern semiconductor industry device. So basically, that means we can easily implement these device structures into the existing devices. So this is a huge advantage. And then for today's talk, and as the research frontiers, a lot of people are talking about or discussing, investigating about the electric double layer transistor and electrochemical transistors because they take advantages of the unique electrochemical reactions. So why people are interested in the interesting electrochemical reactions? Because as you know, as you already heard about the how the synapse works in humans or biological systems, there aren't movements involved. Well, exactly in the electric double layer transistor and the electrochemical transistors, ions are also moving. So using another terminal, which is the third terminal, to control the movement of the ions, can also achieve different conductivity states. Because today's focus of the work would be the electrochemical transistors, so I would just focus on this chemical transistors a bit more. In the slide number 23, I briefly like to introduce you about the three terminal devices and the electrochemical transistors. A typical three terminal devices or typical transistors in our cell phones or computers has three terminals. As I shown on the left, I just named it terminal 1, terminal 2, and terminal 3. The terminal 2 and the terminal 3 are connected with the channel, and the channel would help us to conduct either some electrons to help us to have conductivity. And then the another terminal, or as I shown here, the terminal 1 is separated between the terminal 1 and the other channels by a step insulator, and the insulator helps us or enable us to control the conductivity of the channel by the voltage. So that's why we call it typically a field effect transistor. That means is electrical field uh, electrical field involved, and the electrical field effects gives us the control of the devices. In the semiconductor industry or in our cell phones, the transistors typically has only two states, which is on and off. Basically, it corresponds to the positive voltage applied between the across the insulator, or the negative voltage applied across the insulator if we point. Of course, if we define one the positive direction. And on the left side, that's how it works. When we apply the voltage across the terminal 1, here it shows gate electrodes, and then the electron will be controlled to move up and down, and also the controlled movement of the electron moving up and down gives us different on and off states in the device. And then based on this simple on and off control, eventually we can achieve computation. We can achieve plus, minus, multiply, divided, and even a lot more advanced control. So this is the core device in our again, cell phones or computers. Well, based on this very mature devices, and if we can, in the slide 24, so if we can replace the insulator by electrolyte or by a very unique materials which has ions, then this structure gives us the capability to control the movement of the ion by electrical field, and eventually control the conductivity, or the how much the capability of flowing electrons through the channel we want. And here in the slide number 24, you can see that, for example, on the left side, that's the electric double layer transistor. On the right side is the electrochemical field effect transistor. If you don't know about the electric double layer, that's okay. Well, if you just look at the schematics, by applying voltage between the gate voltage and the blue channel, so there are electrons and the holes, which is plus signs, minus signs can be introduced, or the positive charges and the negative charges electrons can be generated. And there are also circled plus and minus signs. So these are the ions. So they can move up and down, and by how much electrical field we applied, and because it's a movement of ion, we can control the property of the blue channel, and then we can tune it to a different level or different states or different properties. But the difference between the electric double layer on the left and also the electrochemical on the right is whether there is electrochemical reaction, or whether there is a chemical reactions. Well, on the left side in the electric double layer, it's mainly the movement of the ions, but no reactions. Well, on the right side, there are movements of the ions going up and down. In addition to that, there are also reactions. For example, if you can look at the red sign, the red plus sign goes into the blue region, and if there are ions or atoms are pushed into the blue region, so apparently we change the material, right? We change this blue thing, and this blue thing, or we call it channel, will be modulated. So depending on how many the red ions we inject into the blue channel, we can get different properties or different states, or we call it distinguishable conductive states. So if you look at slide number 25, so that's the schematics of the electrochemical field effect transistors. So the structure means we first need to have a blue channels, which is permeable to ions, means ion can be inserted into the channel. Of course, it can also be taken out of the channel in a very repeatable way. And there's also electrolyte, which is the gray electrolyte, which is the one we use to replace the conventional three-terminal device. And this it gives us a lot of iron, give a lot of movable atoms. And the ions are typically positive ions and negative ions, or you can consider it as positive atoms and positively charged atoms and negatively charged atoms. So they can be, because they have charges, they can be pushed into the blue channel or can be taken out of the blue channel. And in addition to that, so the movement of the ion or the injection of the ion creates some reaction, change the blue material's properties, then it change the resistance or change the conductivity or change or we can also call it change the conductive states. So these different states gives us different resistance or different connection strength. So that's exactly how the synapse works, right? So as you say that in human brains, there's the connection between the two ions are synapse, and depending on the connection, let's say connection strength enabled by the synapse, the connections between the two ions can be modulated, and because it's complex networks, the computing is enabled. In order to help Mona the discussion or presentation, I give just two very simple examples, and of course, Monalisha would discuss a lot of details. If we talk about electrochemical field effect transistors applied for synaptic applications or neuromorphic applications, so they are typically liquid-based electrolyte and solid-based electrolyte. And some people use ionic liquid, meaning it's a type of liquid with a lot of ions, positive and negative ions. And some people also use solid oxide, which, for example, may not be oxide, also could be lithium ion solid or ion gels. Then the ions, which could be, for example, could be proton, could be oxygen, or could be even the lithium, can be pushed, injected into the channel or taken out the channel. And look at in the middle, there's a modulation. You can see that depending on how much electrical pulses we give to the system, we can improve the conductance, and then, or we can modulate the conductance to any conductance we want. I can also bring the resistance down to any resistance, any conductance we want. And so those are the so those devices are highly useful for future neuromorphic electronics application, especially the solid-based one, which can be implemented into the semiconductor industry. So that's what we are working on. And but of course, the beginning step is to handle it properly and to learn as much as possible. And we use ionic liquid to start the work, can help us to gain more knowledges and to probe the system easy, because ionic liquid is much easier to handle than the solid based. Of course, the future, the far goal of this topic would be eventually we want to move on to the solid based electrolytes. That's roughly what I want to discuss. I'm not sure there will be questions, but
Uh, and so we can take the question later.
okay.
So let's ask Mona to continue. Then we'll take questions at the end.
Can you hear me?
Yeah. Go ahead. Please go ahead.
Uh, Hello, everyone. I am Monalisha, a PhD student from IISc Bangalore and an exchange student from NTU Singapore. So, after this detailed and nice introduction about neuromorphic computing and synaptic transistor by Prof Prem and Prof Renshaw, I will discuss the experimental work that we conducted for this new study. First, I will give a brief recap of the human brain. So, the human brain is the biological computer and which consists of neurons and synapses. So, we mostly focus on synapse. So, what is a synapse? A synapse is a connection between neurons, and what it does is it allows signal transmission from one neuron to other neuron. And this synapse is really fascinating because it can store and process the information simultaneously. So inspired by that, the main goal of our work is to mimic the functions of biological synapse in electronic devices for neuromorphic computing application. So in this new study, we have designed and fabricated one electrolyte gated synaptic transistor based on cobalt thin film. So in slide 29, you can see the electrolyte gated cobalt based synaptic device. So the important point is that we have used a metallic channel, that is cobalt thin film, for the as a channel for the first time. So usually people use semiconductors as the active layer. However, by using a metallic channel for the first time, we could emulate several synaptic functions and can show that our device is very suitable for neuromorphic computing application. So in slide 29, you can see the cobalt-based synaptic device, which was fabricated using photolithography and Liptok process. The cobalt thin film, which was the channel, was deposited using sputtering. So for this synaptic device, we have used an ionic liquid as the gate electrode. So after the device fabrication, first we measured the transfer curve. So the transfer curve, we got one hysteric behavior. So the hysteric behavior says that the conductance modulation is non-volatile as well as reversible. So these two features of conductance modulation, that is non-volatility and reversibility, is a signature that this cobalt-based synaptic transistor can be used for mimicking synaptic functionalities. So as Prof Renshaw has discussed, this cobalt-based synaptic transistor is an electrolyte gated transistor. In slide 30, you can see that this transistor can work in two modes. One is electrostatic mode, which gives rise to volatile change, and other is electrochemical doping. So that gives rise to non-volatile change of channel conductance. So before going to mimic the synaptic behavior in our electronic device, I would like to give an analogy between the biological synapse and its electronic counterpart, that is synaptic transistor. So that is present in slide 32. So a synapse, which is a connection between two neurons, so the signal transmission occurs by firing of an external stimuli that results flow of neurotransmitter, and finally there is a change in synaptic wave. So in an analogy, so the gate voltage that is applied in the synaptic transistor is analogous to the external stimuli. The mobile ions in the electrolyte is analogous to the neurotransmitter. And finally, the channel conductance is analogous to the synaptic wave. I will tell a bit more about synapse. So the synapse has a fascinating property that is called synaptic plasticity. That means it has the ability that it can change its strength depending on the activity level. For example, if you are working hard or the activity level is higher, the synaptic strength gets strengthened. If there is less activity, then the strength gets weakened. So this synaptic plasticity is very important because this is responsible for all the learning and memory happening in the human brain. So for neuromorphic computing application, it is essential to mimic the synaptic plasticity in our electronic devices. So based on the retention time, that how long this change sustains, there are two types of synaptic plasticity. One is short-term plasticity and other is long-term plasticity. So now we tried to emulate functions which represent synaptic plasticity in our device. First, going to short-term plasticity, that is in slide 34. The short-term plasticity, as the name represents, here the change sustained for a smaller time. So that is presented by two important functions called excitatory postsynaptic conductance and paired pulse fascination. So in excitatory postsynaptic conductance, we fired a positive gate pulse and we see the channel conductance has excited, and after the pulse removal, the conductance comes down to the initial state. So the realization of this function, that is excitatory postsynaptic conductance, is a signature that signal transmission is actually occurring in the synaptic device. Furthermore, we emulated another important function, that is paired pulse fascination. In that, we have fired two consecutive gate voltage pulses, and we see that the conductance modulation caused by the second one is higher than the first one. This paired pulse fascination is used for information processing and pattern recognition in the human brain. So, emulating paired pulse fascination shows that our device is suitable for information processing and pattern recognition in the future. Then we will discuss that we have emulated another important form of synaptic plasticity, that is long-term plasticity, in slide 35. Long-term plasticity is a very important form of plasticity because it actually underpins all the learning and memory happening in the human brain. As it is long-term, the change retains for a longer time and the change in synaptic weight is also massive. So long-term plasticity is emulated via two functions. One is long-term potentiation and other is long-term depression. So in long-term potentiation, we realize that by firing a series of gate voltage pulses, there is massive increment in channel conductance and also the change retained for a longer time. So furthermore, we could also show a transition from short-term plasticity to long-term plasticity by varying the gate pulse amplitude, that is shown in slide 36. So after emulation of synaptic plasticity, which is the basis for learning and memory in the human brain, we tried to emulate the human memory system in the synaptic device. It is in slide 37. So the human memory system is explained by a model called multi-store memory model. So the model says that the human memory system consists of different storage, that is sensory memory, short-term memory and long-term memory. It also says that we can do a transition from short-term memory to long-term memory by repetition of the event. We could experimentally demonstrate the transition from short-term memory to long-term memory in the synaptic device by changing the spike duration. We noticed that with increasing the pulse duration, the non-volatile change of channel conductance is increasing. The non-volatile change represent long-term memory. So the the increment of non-volatile conductance modulation with pulse duration shows a transition from short-term memory to long-term memory in the synaptic device. So after emulation of synaptic plasticity and human memory system, we tried to demonstrate the cobalt-based synaptic transistor can also do processing. In slide 35, we showed that this can act as a high-pass filter. So the short-term facilitation contributes to this high-pass filtering behavior. This was shown by firing a series of gate voltage pulses at different frequencies. We notice that the amplitude gain is increasing as a function of frequency, which shows that it allows passes of high frequency signals easily. So in this way, we could show that the cobalt-based synaptic device can also act as a high-pass filter. So finally, giving a conclusion of this cobalt-based synaptic transistor, firstly, the most important thing is that we have demonstrated one synaptic transistor using a metallic channel for the first time. Secondly, we have shown the interesting cognitive behavior, that is learning, forgetting and relearning of the human brain in the synaptic device. And finally, in the single synaptic device, we have achieved learning, memory and processing. So the learning was achieved by emulating the synaptic plasticity. The memory was achieved by emulating the human memory system, and the processing was shown by high-pass filtering behavior. So with this cobalt-based synaptic transistor also offers one spin degree of freedom, which can be tuned by electrolyte gating to add more features to the existing synaptic device. So with all this, I would like to conclude the talk. Thank you everyone for attention.
Thank you, Mona. So now we take questions. So if anyone wants to ask question, please send a speaker request. We will accept and come up and talk. Any questions? So Alan, please ask your question. Yeah, please go ahead.
Yeah, I'm Alan. Thanks for the beautiful session to Professor Frame and Professor Renshaw and like Dr. Monalisha. I have a question to Dr. Monalisha on the slide number 35. Here, like I have two questions. One is like what electrolyte do you have like used? And second one is like that the conductivity range is like zero point 0.2 microsiemens only. So why it is like low? Can you like improve it with like some other thing? Or I want to know about that conductivity range particularly. Thank you.
Okay. Slide 35.
Yeah.
Mona, the questions are what electrolyte you used first. That's the first question, the ionic liquid.
Yes, so we have used one ionic liquid, that is EMIM TFSI, as the gate electrolyte. And regarding the conductance modulation, so in case of metallic channels, the conductance modulation is a bit lower because of it has intrinsic higher carrier density. So with electrolyte gating, we couldn't increase it that much relatively to the intrinsic value. And furthermore, the values can be improved by working on the device structure. So for us, we have used a thicker thin film, and by reducing the film thickness and also by reducing the channel dimension, the conductance modulation can be improved. So that kind of thing we have also shown in another kind of material, where by working on these things we could improve the conductance modulation.
Yeah, thank you. Thank you. It was nice presentation.
Thank you, Alan. So this is one of the first studies. So we didn't focus on the magnitude of the change, but the changes. I mean, observing these changes and emulating the brain function itself is I mean, huge first step. So we'll be focusing on enhancing the change in the conductivity in the near future. So for that, like Mona said, we have to reduce the thickness of the film, we have to change the width of the channels and so on. So we have to play with the device parameters. Any other question from Ella or Timorous? You may ask your question.
Yes, Professor. Uh, Actually, I had a question regarding this.
Can you hear me?
Okay, Vivek is asking question. Maybe Himaros you can ask later.
Yeah. Can you hear me?
Let Vivek go first. Himaros, you please ask later.
Okay.
Y- Yes, Professor. Actually, my question was related to that. Like, how do you finally come up with a mathematical model? Because you try up with some new electrolyte or something for your channel. So, like, finally, you need a device to create it as a product. You need a reliable mathematical model of the device. So, like, but I think you are in the very early stage, as you told me. My question was regarding that. What challenges will be facing related to coming up with a mathematical model?
Okay, so as I mentioned, yeah, we are in the early stages, but our immediate next step will be like Professor Renshaw mentioned. We should move away from the liquid gating to solid gating. So these tests are done at the laboratory level. So what we do is like we take a syringe and pour a drop of ionic liquid uh, to migrate the ions in and out of the channel material. So this is not practical. I mean, if you want to make a integrated chip, right, you cannot pour liquid into the integrated chip. We have to make a solid gate. So for that, we'll replace the ionic liquid with some materials, probably some oxide, like say tungsten oxide or whatever oxide, right? So those solid gates will be used for sending ions in and out of the channel material. So that will be our next step. And I don't know whether we need to do any mathematical modeling. Why do you think that we should do mathematical modeling?
To get a reliable, like, if you want to produce the same device, like, which will give the same characteristic, so you can verify it using like the voltage current characteristics or something, the relation between the voltage and current, some equations for that.
Manoj, do you have any equations in mind?
Uh,
Or
Actually, to create the device values and parameters and all,
yeah,
maybe.
yeah. Actually, when we do magnetism, we do like micromagnetic modeling and things like that. When we design these synaptic transistors, we don't consider any mathematical modeling. So basically, we need to get reproducible swing in the conductivity, things like that. So we will do statistics probably. Suppose we make 100 devices, how each of the 100 devices behave. So we'll plot the distribution of the uh, conductance swing and so on. That's what we'll do.
Okay. Thank you, Professor.
Renshaw, you have any input? Maybe he's not here.
Thank you, Professor. That's all from me.
Okay, welcome. Yeah. Himarus, please go ahead.
Hello.
Yeah, Renshaw, please go ahead. Do you have any input to the previous question?
But my app crashed for a few seconds, for a few minutes. Yes, I heard the questions about the simulation. For this study, we didn't do any simulation, and from device performance point of view, we think it's not at the stage to do a simulation yet. However, we we can use our results to do simulation. The simulation we are talking about is, for example, the character recognition or the pattern recognitions. So we can, but we haven't started yet. I mean, if you look at the similar studies, they say they published in other papers, they also start to exploring to simulate the real function, I mean, real artificial functions like pattern recognition.
Can you hear me?
Yes.
Yeah. So that was a very interesting talk about synaptic device. Very important insights have been given. My questions will be your choice of materials, cobalt you selected. I know for instance the synapses, the ions are conducted by sodium, potassium, and calcium channels, but your choice of cobalt, I'm quite interested to know why did you choose cobalt. And the second question would be about the neuroplasticity. So will it be useful in clinical situations to treat, like memory loss or dementia in future? Is that your aim or is it something else?
Okay, maybe I answer first, then maybe Professor Renshaw can answer later. Regarding your first question of why we chose cobalt, uh, we are basically working on magnetic materials. So people have studied lots of other materials for the channel. So we being magnetic people, we wanted to see how cobalt will behave, because when we use cobalt as a channel material, we can tailor the current based on the resistance as well as based on some external magnetic field. So we have more knobs to play with the conductivity of the material when we use a magnetic material. So that is the reason why we chose cobalt. Then secondly, regarding dementia and all those things, we are not creating a synapse and neurons for biological application. We are making these devices for electronics applications. Um, so the self correction, all these problems probably will be sorted out in due course. The neuromorphic computing field is just emerging. So at this moment, we are not talking about how what if a synapse fail, how the neuromorphic computing will work out. I think there will be still. I mean, these are not like digital circuits where if one component fails, then you lose the data. But here, I think even if some devices fail, we should be still be able to do the computation, like just like how the brain works. Renshaw, do you have anything to add?
Okay, can you hear me?
Yes.
Okay, great. So, so first I just echo for Prem's answer. So, the group he has adequate expertise on Cobalt-based material. So we would like to start from something we're familiar with, instead of working on something we have no idea of. So that's reason number one. Reason number two is using this. Currently, people are trying to explore different material options. So people, for example, they started working on the polymers, they're working on the semiconductor, they work on the oxide, they work on the different types of materials. And we think cobalt-based material or metallic cobalt is very interesting because it has, for example, magnetism. And also this magnetism we may in future or allow us to do multifunctional synaptic devices. For example, the metallic synaptic devices. So that's another, so multifunctional synapse. And the last option is, to be honest, if you examine different materials, well, for example, the polymers or the oxide-based synapse, the fabrication is very difficult. Why, for example, if you look at the oxide, and it requires high temperature deposition to get a single crystalline phase. It's very difficult, and it's almost impossible to be applied into a fabrication line. And if you talk about polymers, the fabrication is also a little bit challenging. So that's why cobalt has a advantage of fabricating, advantage in fabrications. So we think because of these combinations, it could be very nice territory to explore. So this is my perspective.
Are there any questions?
Thank you, Professor. It was a nice explanation about why you chose Cobalt. I hope you will develop something in the field of clinical, psychology, which helps people with the AI. Good luck to your projects. Thank you.
Thank you very much.
Thank you very much.
Thank you. Are there any other questions? There are no speaker requests, so I assume that there are no questions. So let me briefly wind up saying what we talked today. So we introduced how the electronics industry is moving. Um, so we are moving towards new materials and new architectures, and artificial intelligence is gaining applications, more applications. But the main problem of artificial intelligence is the power consumption. So to overcome the power consumption, we are taking inspiration from the brain, and we are developing brain-inspired computing, which also has the name Neuromorphic Computing. So in the brain, we have neurons and synapses. So neurons process the information, and synapses store the information. And so when we are developing devices, we are trying to create neurons and synapses as electronic devices, which basically should emulate what the neurons and synapses do in the brain. So today's talk, we talked about synaptic field effect transistor, which is basically a three-terminal device. So we have a source, we have a drain, and we have a gate. So basically, source is the place from where electrons will flow, and the electrons will reach the drain, and we can control the electron flow using the gate. So that is the field effect transistor. Just like how we control the water flow from the tap to the drain. So we use a water tap, the the knob in the tap to control the flow of water. So similarly, we use the gate voltage in the synaptic field effect transistor to change the flow of electrons. So in the synaptic field effect transistors, what we do is we apply a gate voltage and send ions into the channel material. Channel material is the material that's placed between the source and the drain. So we change the resistivity of the channel material. So unlike the binary systems where we have states of 0 and 1, in this synaptic field effect transistors, we can have multiple resistance states. So we can have not only 0 and 1, we can have many other intermediate states. So we can start from 0, 0, 0, 0, go all the way to 1, 1, 1, 1. So in this case, there will be like 2 power 4 states. So we can have multiple states, and that's what we need for synaptic applications. So we prepared this kind of synaptic field effect transistors using cobalt as the channel material. So by ionic liquid gating, we change the resistive state or conductive state of the channel material and shown brain-like behavior. So Monalisha described that we can show that plasticity, long-term plasticity, short-term plasticity, and so on. So this can be emulated in our synaptic field effect transistors. So this is the first step. So we are using liquid gating. So we'll move to solid gating, and we'll also make smaller devices and so on. So that will lay the path for neuromorphic computing. So with this conclusion, we end our session. Thank you very much for attending. So this is our first space. So there may be some issues. If you have any feedback, please give us. So we'll have more space probably the last Friday of every month or something like that. So NTU Physics will try to organize more such spaces. Thank you for participating. Good night.
Bye bye. Thank you very much. Thank you, everyone.
Thank you all. Bye.